Okay, welcome to week 6. Here we're going to say a little bit about modeling, although frankly at this late stage in the course it's a little bit difficult to know what to say, since it would be easy to spend an entire semester talking about nothing but modeling, and to some degree it's just one component of what we're trying to do in this course, which is developing an understanding of a data set or more than one data set and getting a good feeling for the data set and how to create interesting questions about what's going on with the data set. Modeling is one component of that, but not the only component of that. And in my own long, sad experience, it's very often the case that the real data that you get from some client in like a consulting scenario, the real difficulty is just understanding what in the heck is going on with the data, cleaning it, organizing it, getting an understanding about what the fields actually mean and whether the fields that are unique really are unique and things of this kind. And then once you fight your way through all of that stuff, then choosing a model and running a model typically is pretty straightforward. Then it's just somewhat surprising if your model turns up statistically significant results. All right, well, so that's my bitter and cynical view on things, I guess. In a nutshell, if you're doing things like physics or chemistry, where you're dealing with vast numbers of mindless little components, then statistics works astonishingly well. And when you get into biology and diseases and things like that, statistics also works pretty well most of the time. And when you get into things like logistics and economics and finance and psychology, things tend to not work tremendously well. In finance, which is an area of particular interest to me, things are particularly horrible because here you have a situation where the people who are doing the statistical tests are the people who are trying to benefit from the statistical tests. So in effect, you have this population of people who are watching themselves trying to gain an edge on what everybody is doing based on statistical analyses that, for the most part, everybody else is running. Anyway, okay, so the textbook does an astonishingly good job of describing modeling at the right kind of level for what we're trying to do in here. And so I really heartily recommend that you take a look at the modeling section in the textbook. I think it's chapters. Well, let me pause for a moment. Yeah, chapters 22, 23, 24. And if you go through that, you'll have a very good idea about approaches that you can take with the data that you're working with. Hopefully, the data that you're working with, which you've downloaded from some website, is in a little better condition than a lot of the kinds of data sets that I have had to deal with, things like logistics and predicting failures of machines and spreads of pollution and water systems, blah, 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 blah. It's very, well, messy stuff. Anyway, so what I've decided to do is to just kind of give some general thoughts about things, and also in the book, in the first of the 3 chapters about modeling, they do a really delightful, pretty much totally intuitive, pretty much non-mathematical approach to selecting a linear model that's appropriate for the data that you have, and doing this using an optimization function rather than doing some calculus and linear algebra to get an analytical answer for the least squares regression. So that's great stuff, but I did want to just say something about the analytical solution, and then just make some observations about things to be concerned with your models. Okay, so why do we do modeling? Well, we want to get some understanding of some population that we're observing, to be able to describe that population in some way that supports decision making in our case. Some kinds of analysis, like clustering analysis and so forth, just groups things together in a way that hopefully increases your understanding of relationships among the various parts of your data set. But we want, in our context, to be able to make decisions about things that will hopefully improve our life or somebody else's life going forward. Okay. So we're going to be concentrating on what's called predictive modeling. And in predictive modeling, each of the observations that we have in our data set has got some outcome variable, or also sometimes called some label variable. And in fact, if the data set has multiple columns, it's often the case that you can pick one of the columns to be your outcome and then try to predict that particular column, that particular variable, based on the other variables that you have. So in fact, your data set, depending on how you choose to analyze it, may have multiple different outcome variables that you can try to predict. So in essence, what a model is just a function that you feed so-called independent variables values into, and that turns the crank and produces a prediction about the outcome variable. Now, models are always approximations, typically very simplified approximations, and you have to be aware in your mind of the assumptions and simplifications in your model. One of the great problems with any kind of statistical modeling, particularly in the social arena as opposed to biological or physical, is that you can oversimplify things and persuade yourself that you're still doing good stuff. For example, now you may not, but I remember painfully the financial collapse that occurred in 2008, which was basically based on mortgage derivatives on U.S. household mortgages that had been designated or predicted to be of much lower risk than they actually were. pretty much everybody believed at that time that real estate prices could not go down except for locally. That it would be possible for one or two or three cities to have a local real estate collapse, but this just wasn't in the cards on a national basis. And thanks to the central limit theorem, which says that the means of samples from any population are normally distributed, you can do sophisticated mathematics to take samples from distributions that are not normally distributed and persuade yourself that your sample can be thought of as normally distributed. Now, if you push this to an extreme and base prices of derivatives on this kind of analysis, the upshot is that what you're claiming is normally distributed is actually got a much wider, much thicker tails than a normal distribution has, and the derivatives that you're pricing at a certain assumed risk actually have much higher risk in them. And this is what happened starting in 2007 and then really collapsing by 2008, was that subprime mortgages started failing left and right and up and down and sideways, and there were countries that nearly went broke as a result of having invested in this United States mortgage debt stuff. So I guess what I'm trying to get at here is when you're applying models to data, make absolutely certain that you're not lying to yourself, that you're not trying to find some kind of statistical excuse for doing something that, if you think about it coldly and unemotionally, at the end of the day is just not going to make sense. All right. So having said this, it is nevertheless the case that in the short to medium run, having some kind of model is essentially always better than guessing. You just have to bear in mind that your model does not describe the world. The world is the world, and the world does what it does, and your model is an approximate description of part of the world, basically. Okay. All right. So in order to pick a model, that is, in order to pick a function that you can apply to try to predict an outcome based on certain other observations of certain variables, the very first thing you should always do is to look at your data by applying a scatter plot. And then from that you can usually tell, is there an approximately linear relationship between a couple of variables? Is there an approximately quadratic relationship or cubic relationship? Is there an approximately exponential relationship? This kind of thing. And you can't just look at the shape of the graph and say to yourself, oh, well, that's cubic. You have to have some intuitive reason for thinking that it ought to be cubic. Hopefully. You should not just, not just throw up a scatter plot and say, and look at the shape of the scatter plot and say, oh, well, that's cubic. There's got to be some underlying reason why you thinking it's cubic makes sense. In any case, once you've decided whether the relationship between the variables that you're trying to compare is linear, quadratic, cubic, exponential, whatever it might be, you simply write down a parameterized version of an equation of a function, and any outcome that you think is a polynomial or exponential result of some input variable or variables, it turns out can be converted into a so-called linear equation in the parameters, not in the underlying observation variable itself. All right. So in other words, if I have a linear relationship between some outcome y and some observed variable x, what that means is that we think that we should be able to describe y as some parameter alpha plus some parameter beta times x. And what we're looking here for is the best alpha and the best beta that gives us the best predictions based on the series of x and y observations that we have in our available data set. Now, for quadratic, on the other hand, we might have y as some parameter a plus some parameter b times x squared. That doesn't look very linear, but when we're talking about linear, what we mean is it's linear in the parameters. It's linear in alpha and beta. It's not linear in x, okay? Because we can just replace. We have observations of x and we have observations of y that go with those x's. We can basically just square every value of x that we have and call that variable z, and then we have that y is alpha plus beta times z, so it's still linear in alpha and beta. Similarly, if we have an exponential relationship, which is what we would expect to see in things like virus outbreaks, at least until the virus outbreak is brought under control in some way, we would expect to see exponential growth. Or if we're investing in stocks, we certainly hope that the value of our stock increases exponentially over time. By taking the log of both sides, once again, we can turn this into an equation that is linear in the two parameters, alpha prime here and beta. And then we can just use ordinary least squares to figure out what the good values for the parameters are. Okay, and so this is the part that in the textbook they do on a purely intuitive level by just trying a whole bunch of random lines and then picking the best ones from among those random lines and then trying to refine and refine and refine those guesses. Okay. In particular, what we're trying to do here to identify the best parameter values is to minimize the variance between the predicted values and the observed values. And this difference between a predicted value and observed value is what's called a residual. It's the difference between what you actually observe and what you predict that you should have observed. And to get the residual, which we're just calling epsilon sub I for observation I here, this epsilon sub I is the error term. It's the amount by which we are off on a given observation. Okay, so for a given observation of yi and xi, if we believe that there's a linear relationship between yi and xi, then we would write yi is alpha hat, that's our estimate for alpha, plus beta hat xi, and then there's going to be some error term for that particular observation.
from the given estimated parameters alpha hat and beta hat that we choose. Okay, so we just throw the error term, the residual, on the left side of the assignment and put all the other stuff that we either know in the case of yi and xi, or are trying to compute in the case of alpha hat and beta hat onto the right side. And now we decide, okay, we want to minimize something about these residuals. And here we have a choice about what to do. We could decide that we're just going to compute the magnitude of the residual. We don't care whether it's positive or negative. We're just going to compute the magnitude. And we're going to somehow try to minimize the sum of the magnitudes of all these residuals by choosing some appropriate alpha and beta. The approach that they use in the textbook would actually allow you to do this, because they use an optimization function to get out your parameters, alpha hat and beta hat, basically regardless of what function of these residuals you're trying to minimize. I say basically regardless. Well, it has to be it has to be something that has a unique optimum solution, and it's possible that you won't have a unique solution. Okay, well, as we ought to know, in normal statistics, or in conventional statistics, we define this thing called the variance of some random variable to be the expected value of the difference between the random variable and its mean. Okay, the expected value of x is, you can think of that as just being the mean of x. So x minus the mean squared, the expected value of that thing is how we define the variance. Okay, we could define the variance, the amount by which an observation differs from the mean, in some other way, but like using an absolute value rather than a square. But it turns out if you do use this particular formula for computing the variance, a lot of calculations get to be really easy. It's easy for us to minimize the variance of the residuals just by taking derivatives and doing some linear algebra to get a minimized sum of the squared residuals. Okay. Now we also define the covariance between two different random variables, x and y, to be the expected value of x minus the mean of x times y minus the mean of y. Okay, so that's just a definition. It's a definition that turns out to behave nicely mathematically. And if we define the variance and the covariance this way, and let me back up a minute here. Okay, so we have this equation for what the residual is. We've decided that we're going to square the residual, which means, of course, we're squaring the thing on the right side of this assignment as well. And we're trying to figure out the minimum, the values of alpha hat and beta hat that minimize that sum of the squared residuals. Well, in order to minimize something, we can take the derivative, in this case the partial derivative with respect to alpha hat, and also the partial derivative with respect to beta hat, we can set those partial derivatives to 0, and we end up with a system of linear equations that we can solve to figure out what alpha hat and beta hat should be in order to find that minimum, that point where the derivative is, where the partial derivatives are 0. And I was going to write down a whole bunch of algebra, and I decided that was stupid, because you can look that up online. And what we end up with is that beta hat is the covariance of x and y divided by the variance of x. And here we've written out the actual sums used to compute the covariance and the variance based on the actual observations that you have. Now, fortunately, this makes some intuitive sense. The beta hat is our slope, okay? So beta is our slope in our linear equation. Whoops, didn't mean to highlight that. There we go. So beta hat is our slope in our linear equation. And if we think about how a scatter plot is going to look, we've got x on the horizontal axis, and we've got y on the vertical axis. Now, the horizontal axis, we have a certain spread for x. And the variance of x, you'll notice, is in the denominator for this beta hat computation. The variance has the nice property that it can never be negative. The smallest that the variance can be, if every single observation is exactly on the line, the smallest that the variance can be is 0. So the variance, if there's a lot of variance, the variance is going to be large. If there's less variance, the variance is going to be small. And you can see that as the variance decreases, that slope is going to increase. Okay, so that makes intuitive sense. The more spread out the x's are, the shallower the slope is going to be. And the tighter together the x's are, the higher the slope is going to be. Now, the covariance, on the other hand, certainly can be negative. And if it's negative, that means that you're going to have a negatively sloped line. If it's negative, that means that as x increases, y tends to decrease. Okay, whereas a positive covariance means as x increases, y tends also to increase. Now, it's possible for that covariance to be close to 0, meaning that the slope is totally flat. Or it's possible for the increase in y to be very tightly correlated with x, and for the slope to be larger and positive. All right, so what am I trying to say here? So it's not intuitively clear that you're going to get beta as the covariance of x and y divided by the variance of x. But it is easy to remember, relatively speaking. I mean, it does make intuitive sense, because you would expect as the variance of x narrows that the slope is going to increase, and you would expect that as the covariance increases, that the slope is also going to increase. Okay, and then alpha just falls out of knowing beta. Alpha hat is just the mean of y minus beta hat times the mean of x. Now, once we've derived this parameterized, these parameters for the least squares, we can then compute a bunch of statistics on how good the fit of this line is. We'll get p-values for alpha hat and beta hat. We'll get an r-squared telling us what fraction of the variance in y is caused by or is due to the variance in x, et cetera, et cetera. Now, for us, we're just going to ignore. You should compute this for your analysis, but we're not gonna dwell on these results. Now, one of the most important things that you need to do when you apply a model is to avoid what's called overfitting your data. The models that we've looked at here only have 2 parameters in them, and they're pretty simple, a line or a quadratic or an exponential. We do have way more data than just 2 observations. And so we could get carried away and say, well, look, I've got 200 observations here. Surely I could get a much better fit and make much better predictions if I make my model more sophisticated and add more parameters. But this quickly leads to what's called an overfitting problem, where you start incorporating the random noise in the observations and treating that as part of the actual so-called signal that you're trying to see in your data. The most ultimate ridiculous model to use is a model where you just directly connect the dots on your scatter chart, on your scatter plot together, and get yourself a variance of 0. Okay, now a variance of 0 sounds, or I should say the variance of the residuals, the squared residuals. You can get that down to 0 if you create a sophisticated enough model. But I hope it's intuitively obvious that that's actually not going to be very good at predicting new outcome values based on new observed values. Way back in ancient history in a finance course, one student that I saw, we had something like 150 days worth of data about stock prices or something of the kind. And what this fellow did actually was not overfitting the data. What he did was the equivalent thing of what I call overfitting the model. Okay, so he understood that having over-parameterized models was a bad idea, but he didn't somehow grasp that this meant that having many simple models with a small number of parameters and throwing this huge number of simple models at this set of data was really the same problem with just a different face on it. So we had something like 150 data points, and this fellow generated over 200 simple models and tested the data points using more models than there was data. The problem here is that if you keep trying models purely at random, just by luck, you're going to find a model that really fits that particular data that you have. But that also is going to turn out probably to be a pretty bad model for estimating outcomes based on new observations that you make. Okay, so and apparently this is a problem now in medical research as well, that when people are, for example, attempting to develop new drugs, there's a tendency to throw a whole number of tests at these drugs, and if some test pops up as being statistically significant, then getting all excited and saying, "Oh, we really found something here." And there's actually been a push in the medical literature for decreasing from calling something significant with a value with a p-value of 0.05 and dropping it down to a p-value of 0.005 because there's too much of and I'm sure I read this somewhere, but I can't find it, of what I call model shopping, where you just throw model after model after model at a set of data until one of your models accidentally turns out to be a good model for that particular set of data. Okay. Another comment I wanted to make was what you should do about outliers. And what you should do about outliers is you should think about them very carefully, and you should try to come up with some understanding about why those outliers may be in there. You cannot simply decide that you're going to throw away certain outliers. You have to have some reason for wanting to throw these outliers away. And so here I've made up a data set. I'm imagining that we have just discovered the mauve-crested billabong bats in some location in Australia, and we dispatch 20 field biologists to this location to get some statistical information, to get some data about these newly found bats. All right, so one of the things that they measure is the adult wingspan in centimeters, and we get back the data from these 20 biologists, and we plot the data, and we see a distribution that looks, well, literally kind of normal right here. But over here, there's these weird outliers. And you know, what is that about? What are these readings? Looks like the average wingspan is, 78, 79, 80, something like that. And yet here we've got these wingspans down in the low 20s. What the heck's going on there? Well, so a little investigation, and we discover, one of these biologists that we sent out to do these measurements was an American, and the American measured things in inches rather than centimeters. Whoops. So here we do have a measurement error and or a data entry error. And so in this case, we would be entirely justified in just tossing out all these values below 40 and computing our mean and standard deviation and so forth based on the other values that we have. However, sometimes you absolutely must not throw out outliers. And as an example, I guess I should flip to my other side here. One of the assumptions that we make in finance when we're tracking things like stock prices is that the stock prices over time will rise exponentially. And consequently, if you take the log of the stock price returns, it's what am I trying to say? It's a reasonable assumption. It's a fair assumption. It is assumed, for simplicity's sake, that these log returns have a normal distribution with some long-term mean return and with some standard deviation of log returns. This is what's called a log normal distribution. We say that the returns on a stock are log normally distributed. All right, so as an example, I pulled down some recent closing prices for Tesla stock, Here we have the date, and here we have the closing price for the stock. Now, the return from one day to the next is the closing price today divided by the closing price yesterday. Okay, so if today's closing price is higher than yesterday's closing price, then we have a return that's greater than 1. Okay, so for example here, although we don't have data for April 13th, that must have been a Monday. So we don't have data for April 10th in the table, but apparently we had about a 13.6% return on the closing price from Friday relative to this Monday, which is a pretty darn big daily return. Okay, now we take the log of all of these things so that the logs then are assumed to be normally distributed. And if we plot that, and this is for an entire year, it's about 254 days. Here's the histogram that we see. And now we look at this and we ask ourselves, does that look like a normal distribution? Not really. Okay, we've got an awful lot of values of big returns and big positive returns and big negative returns. Well, if we were just casually looking at this data and not thinking carefully about what the data represented, we might think, okay, well, let's just toss out these outliers and just use the main part of the returns here so that we can get some estimates about average return and standard deviation of return and so forth. But in this case, that's a ludicrous thing to do, because it is in fact out here on the tails of the distribution where the most amount of money is either made or lost. There's no money being made or lost on returns of 0, okay? But there's a huge amount of money being made out here with the big returns, and there's a huge amount of money being made out here with the small returns. And this is real data. This is not data that we want to throw away. So here we would conclude, and of course we should run a statistical test to show this, but we would conclude that no, this is not really normally distributed. It's probably not a great assumption that this stuff is normally distributed. It's messier, fatter tail distribution than normal, and all the nice math that we can do using the assumption that it's normally distributed, well, that nice math is also wrong. Now, I should also point out here, of course, that we've just gone through this vast stock market volatility just over the course of the last month because of COVID-19, and so it's likely that in years that if I had looked at a year's worth of data from January to January instead of from April to April, it's quite likely that the distribution from January of 2019 to January of 2020 would have looked more normal than this does. But again, this is like the stock market equivalent of a volcanic eruption. Doesn't happen very often, but it does have a big impact when it does happen. And finally, here on slide 17, this is a quantile plot also showing that close to 0, okay, things look pretty normal right around 0 returns, but the tails of the distribution are quite a bit thicker than normal. And what that means is that you have a much higher probability than the normal distribution would give you of both making a bunch of money, but also, unfortunately, of losing a bunch of money. Okay, so I just wanted to make these remarks about things to avoid and things to be careful of when you're looking at any data set. And I encourage you, for more details about how to go about applying models using the tidyverse libraries, to do take a look at the relevant chapters in the textbook. I had intended to write a lot more stuff. I kept writing stuff and throwing it away, and I just realized that there wasn't any way that I was going to be able to approach the level of detail and level of specificity of what's shown about the tidyverse in the textbook itself. So I'm just gonna refer you to that for further details. Okay, well, take care. I hope you are all well and safe. Take care.